Hello friends, welcome to my channel. Let's have a look at problem 242, valid anagram. This problem is an easy problem in LeetCode, and this is actually a follow-up problem for problem 438, find all anagrams in a string. So you are welcome to check out the previous video or the video for problem 438. And in this video, we're going to examine this problem and explain several solution formats. So first, I'll read through the short statement, and then we look at the codings. Here, the statement is as follows. So given two strings s and t, return true if t is an anagram of s. Otherwise, return false. So here are two examples. In the first example, s and t are anagrams, so we return true. In the second example, we return false. For example, c in t does not appear in s, therefore the two strings cannot be anagrams, so we return false. So here the constraints are the following. First, the two strings are not empty, and their length is bounded above by 5 times 10 to the power 4. And secondly, s and t consist of lowercase English letters. So we're going to use this second one in some way, and also we're going to use these numbers. So with that said, let's look at the solutions. So for the first solution format, so we're going to use this comparison. So here we can use dictionary, or we can use a list. So first, let's make a solution. So we want, if s and t are anagrams, so we know the unique letters in s and t should be the same as a set, and then the corresponding frequencies should be equal. So this results to compare the counters or the dictionaries of these two strings. So we're going to use counter s, and then we're going to compare. So if these two counters with respect to s and t are the same. So here essentially we are doing dictionary comparison, but this is one solution. Now let's first do a check. It passes one example. Now let's look at the generic case. It passes all the generic cases. So this is the one solution format. So now let's change a little bit, but we are using essentially the same idea. So in this V1, so we are using comparisons based on dictionary. So actually we can encode s and t to be a vector, right? By the problem assumptions. So here only lowercase English letters appear. So there are 26 lowercase English letters. So actually we can make a s list and t list. So which actually we can understand them as a 26 dimensional vector. Then what we're going to do is to iterate over s and t, and then so we are going to increment corresponding counting in the corresponding components or positions. So this is actually very routine. So for character in s, and then we're going to count the corresponding position. Let's see. So index, so A corresponding to 0 and B corresponding to 1. So it's nothing but the ordinal number is shifted by 97. So we're going to increment this position by 1. And then similarly, we iterate over T. Let's copy this one. Let's for loop. And then we're going to iterate over T. So this way we get two lists, s list and t list. So actually we can regard them as two vectors. So we want to make sure the two vectors are the same. So in other words, we want to compare s list and t list. So this forms another solution format, but here the comparison is based on vector or lists. So with that said, let's first do a check. It passes one example. Now let's look at the generic case. It passes all the generic cases. So now let's mark this solution as V2 and present another solution. So here, the third solution is based on the observation that if S and T are anagrams, then after we do sorting in the natural order, so this should correspond to the same result. So here, essentially, we are comparing two lists again. So here, what we are going to do is to use this sorted, so S. So then this sorted will return a list of characters. And then we need to compare this with sorted T. So this is another solution. Let's first do a check. Yeah, it passes the generic cases. So now let's call this solution V3. And then we're going to use another solution. So for the third family of solutions using hashing, so essentially we follow the idea of wrapping cap pattern matching algorithm. So you can also check out problem 438. So here we're going to use this number. So first, let's make some simple computation. So we notice that log 2 of 5 times 10 to the power 4. So this number is actually equals to log 2 5 plus log 2 10 to the power 4, right? So the first number, log 2 5, is less than 3. And the second one, so we can actually change this to be 4 times log 2 10, which is less than 4 times, because log 2 10 is less than 4. So this is 14, so which is bounded by 19, right? So we can see it's less than 90. So we can use use this as a separation of bit positions. So let's look at this solution. So here, actually, first I want to get a hashing table. So this is for all the lowercase English letters. So we can get that using the string lowercase, ASCII lowercase, right? So then we can map this character to a bit position. Let's say 2 to the power. I'm going to use 20 times I. So this 20 is a separation gap. And then we're going to, for I, character in string ASCII lowercase letters. So this thing is nothing but A, B, C, D up to Z in a string. So this way we have a hashing table. And then we just need to check if S and T have the same hash value. So notice that for this method to work, here the specific hashing technique is important. We need to make sure we design hashing that makes this work. Or so here, let's first get the hashing hash value of S, which is nothing but sum of D character for character in S, right? So notice that because of the way we do the hashing, so positions of the character in S does not come into play. So similarly, hash value T, so it's nothing. Let's copy this one, but change the S to be T. And then we do comparison. So return whether hash value of S equals hash value of T. So this is the third solution format, or fourth one. So let's do a check. So not enough values to unpack. So here character for I. So here let me write enumerate string S. Yeah, so it passes one example. Now let's look at the generic case. So yeah, it passes all the test cases. So actually, if you think a little bit deeper, so this solution actually is essentially the same as solution V2, but it's a little bit general. It has many other applications, so you can check out the wrapping cap pattern matching algorithm, and the another one related is the so-called KMP algorithm, right? Kuss-Morris-Pratt algorithm. So with that said, actually we finished presenting the different solutions to this simple problem. As we mentioned, we regard this problem as a building block for other problems. So with that said, you're also welcome to follow up and check out other videos in my channel. So we're going to have another video related to Anagram. So please follow up. With that said, that's it for this video. Thank you.